If you have ever run a computational fluid dynamics, or CFD, simulation, you know the frustration. CFD relies on numerical analysis to solve fluid flows, and frequently, the residual spike, the solver fails to converge, and the complex 3D mesh violently distorts into a screen of error warnings. Successful aircraft do not always require this level of computational precision. The HESA Shahed 136 operates at the extreme low end of the aerospace spectrum, earning the nickname flying lawnmower for its unrefined approach to flight. The physical footprint of this drone is small. It has a wingspan of roughly 2.5 meters, a total length of 3.5 meters, and a weight of approximately 200 kilograms. While high-performance UAVs rely on bespoke, sensitive hardware to achieve altitude and speed, the Shahed 136 utilizes low-specification, off-the-shelf components. These parts are easily sourced and distributed through global supply chains. This pragmatic design centers on the propulsion unit, an Iranian-made Motto MD-550. Analysts believe this is a reverse-engineered four-cylinder piston engine, thriving a two-bladed wooden propeller in a rear pusher configuration. This engine produces a loud acoustic signature and limits the drone to a very low airspeed. However, the design yields a staggering operational range, estimated between 1,500 and 2,500 kilometers. This range is dictated by Voscoil's endurance equation. In this model, flight time in cruise is maximized by a large fuel fraction and low wing loading, the total weight of the aircraft divided by its wing area. Speed is sacrificed to maximize these two specific variables. The Shahed 136 is built for aerodynamic pragmatism. It is a tool designed to overwhelm air defenses through numbers and low-cost endurance, bypassing the need for expensive stealth or high-speed performance. Aerospace design typically reserves the delta wing for high-speed flight, such as the sharp geometry found on supersonic interceptors. In the Shahed's subsonic regime, the delta wing serves a different purpose: massive volume efficiency. The thick triangular shape provides a large internal cavity to maximize fuel storage. This chart demonstrates the concept of the lift curve slope, which measures how rapidly an aircraft's lift increases as its angle of attack changes. A conventional straight wing has a steep slope, reacting sharply to the air. The delta wing has a much shallower angle. A smaller lift curve slope makes the aircraft less sensitive to vertical wind gusts. The drone remains indifferent to small atmospheric disturbances, providing a stable platform during its terminal dive. Terminal attack phases are vulnerable to turbulence, which usually requires fast-acting control surfaces and complex software to keep a munition on target. The delta wing removes this hardware requirement. By pairing high wing loading with a low lift curve slope, the physical geometry provides flight stability, allowing the drone to operate without sophisticated flight control systems. Because the drone lacks complex launch avionics, it uses a truck-mounted rail system and rocket-assisted takeoff, or RATO. A solid fuel booster provides the initial acceleration before the piston engine takes over. This mobile, compact launch method makes tracking an attack's origin difficult. Standard long-range missiles often rely on massive, detectable static launch facilities. The Shahed proves that an airframe's geometry can be designed to ignore environmental noise, reducing the reliance on onboard computers.